Key ideas. Well, really, we've used two equations. And again, by the way, you can write this down if you want to, or I can print this up afterwards. I'm going to be doing lots of cutting and pasting of circuits, so it may be faster to watch and write and have me print this up for you after. Two key equations. Now, there is a third one. We did define current as how much charge is flowing past any one place per second. It's how fast charge is moving. We haven't used it that often. I'm pretty sure there is at least one question on your test where you are going to have to use that. And you clue in because it talks about amperage and it either asks for or talks about coulombs, charge. Then, you know, like, oh, or it asks time, because I think this is the only equation that has time in it. But the two main ones have been Ohm's law and Joule's law. There's a good sneeze. And remember, you can substitute into here. So you can substitute IR in for the V, and you'll get IIR, or I squared R. You can get the I by itself and substitute in for the I, and you'll get that too. Okay? Then the second key idea we had was my ski hill analogy. If you've wrapped your brain around most of that, that'll bail you out of 99% of what we're doing. In fact, I would argue it bails you out of 100% of what we're doing. It'll even bail you out of most of your first year university stuff, as it turns out. This was really Kerkhoff's rules defined in terms of the ski hill analogy. What were the two Kerkhoff rules? Current in equals current out, and this was technically a conservation of charge. Conservation. It's saying those positive charges that don't really, oh, for Pete's sakes, the positive charges that, as far as I'm concerned, are moving, don't vanish. They got to go somewhere. Okay?
Miss Sarah,
and we also have a second one.
Thank you.
Kerkhoff's second rule for voltage was if you complete a loop, you end up at the same height. Oh, wait a minute. Cross out the word height. Voltage. But the analogy I used for this whole unit was I said voltage was very, very similar to height. Okay? Make sure you understand current is which way positives flow. Electron flow is in the opposite direction of current, and that's really what's going on. But hopefully by now I've convinced you why we like to let downhill be positive. Megan, could you shut that door back there for me, please? I got a student writing a test back there. I thought I had closed it, but I must not have. Thank you. If you had this, then in my mind, everything fell out of this. Now, we also had the rules for series and parallel resistors. I didn't prove those with you because I think we had an assembly in one of the blocks that day, and so I was stuck with a short class. They actually pop out quite nicely out of Kerkhoff's laws. It's very easy to prove. And then the last thing we talked about was terminal voltage, which we called the little bump at the end of a chairlift, which really was a battery. So let's look at some stuff. I think the best way to jump in is just to do some examples, and then I'll also go over any weird ones you're wondering about from the big review package. Sure, this one will work. Terminal voltage. Because the reason I'm starting with terminal voltage, it seems to be what in the past kids have struggled with the most. This is from our old review that I haven't given you yet. This was a multiple choice, but we'll treat it as a written. It says, what's the terminal voltage in the cell shown below? The terminal voltage, which we usually write, it's your EMF, which is your maximum theoretical voltage, the constant voltage. This battery has a voltage of 4.5 volts always in theory, minus whatever you lose going through the battery. But instead of writing voltage, I wrote I times R, because I times R is interchangeable with Ohm's law of voltage. Little r, the internal resistance. So what this question is really saying, what this question is really asking is, hey, what's the terminal voltage here? That's the equation on your formula sheet, but can you see really what it's saying is how high between here and here? The height is 4.5 minus what you lose going through that little resistor, because we said when you go through resistors, that's downhill, minus 0.8, 0.63. Right? Where'd the 0.8 come from? Total current. By the way, what's the current in each of these 10 ohm resistors? 0.4. Which means, what's the voltage in each of those 10 ohm resistors? How many volts do you lose? Go I times R in your head. 4. You know what? I really didn't need to do that, because if I had the terminal voltage, which ends up being 0.8 times 0.63, 4.5 minus 0.504. You know what? The terminal voltage is 4 volts. This voltage right here, if I combine the bump, my chairlift actually isn't 4.5 volts high. It's actually 4 volts high if I include the little bump at the end of the chairlift. So how high is each of these one hills? 4 volts high. I could also get it independently that way, or I could reaffirm, I could have found the terminal voltage by just going, well, since that's there's only one hill that everybody goes through, they can split up, but everybody only goes down one single hill. That one single hill's height has to be the terminal voltage. Okay. Let me look at another one here. Apparently I liked 25. Why did I like 25? Well, hey, let's try this one. 23. We'll just do some and you can talk me through them. I don't think you guys have this one on your actual review. And a little twist, asking you to find a resistor. Okay. Again, our strategy is always, if you know 2, you know 4 things. And to start out, we're like, hey, did they tell me total current somewhere? If they did, that's my starting point. And if there's anywhere they told me 2 things. So help me out here. Any suggestions? You know what the very first thing I would do? First thing I would do was, because it gets me writing and it's easy, that's downhill. And I know the current going through the battery, the total current. Jake? 2.4. Now I'll follow it. Oh, let's put an amps there. Follow, 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 follow. Oh, and I know how many amps went that way. How many amps went that way? Sorry? 0.6. How many amps went this way? In your head. Kevin. Sorry, Yu-Chen. 1.8. 1.8 amps. Oh, I now know 2 up there. As soon as I know 2, I'll fill in the third one. By the way, power I only do if they're talking about power or if they want power. But it is still true. If I know 2, I know 4 things. I'm always interested in the V and the I and the R. So now I know the voltage drop across there. It's going to be 1.8 times 5. Voltage 3, since it's resistor 3. 9 volts. Does that tell me anything? Something else I now know. Can you use a number, R1, 2, 3, or 4? And
R1 plus R2.
oh, these add to 9 volts?
No. The voltage.
You said R1 plus R2 is 9 volts. Is that what you said? Yeah, that's totally, absolutely good. Oh, and I know 2 down here as well, don't I? It's 6 times 0.6. You know what? This is 3.6 volts, and you've just told me, how do you know, by the way, that they add to 9 volts? Because if we can shake hands and meet up, there's my analogy, they must go down the same drop in height. So this must be 5.4 volts. Oh, do you know the current in R2? Page what? 0.6 amps. I know 2, I know 4. I can now say R2, R is V equals I. I don't do this one very often. V equals I times R. R equals V over I. Voltage divided by current. Well, 54 divided by 6 would be 9. 5.4 divided by 0.6, I think it's also 9 ohms. In terms of, if I was marking this, what was this one worth on the original? 5 marks. I would probably do something like this. I would look for either in the written work or just labeled on your diagram. I'd probably give you 1 mark if I saw that, 1 mark if I saw that, 1 mark if I saw that, probably 1 mark if I saw that, and then 1 mark for the answer or something like that. Easy peasy. How else, because this is a 5 marker, what could I ask as a part B? What did they ask? Oh, calculate the power. You know what? I know now I know V times I, or I could go V squared times R, or I could go I squared times R, or sorry, V squared over R. I could get the power, no problem. Hey, they might even say calculate the total power in this circuit. By the way, power itself is a scalar. If they ever ask you for the total power, it's just add them all up. Don't worry about parallel or series or whatever. What they're really just saying is how many watts to operate this machine. Okay. 25. And we'll change the question a little bit. So, copy it, Mr. Dueck. Click. And this is how I make up a lot of your tests. All I do, so if you work through the review, you'll have seen 99% of what's on the test. And all I do is I take a question and I go, nah, nah. Let's have a current of, oh, I don't know, 0.35 amps. 0.35 amps. And there, now it's a brand new question. The only risk in doing that is I may have made up an illegal circuit. So we'll hope I haven't. If not, I would not give you that question. I would try it. I think there is a question on your test where I am going to ask you to find little r in some kind of a... Well, you know what? I'm going to ask you to find a resistance somewhere, whether it's the one we just did where we had to find resistance number 2 or the little internal one. You know what? This one's actually not so bad. It hasn't got a bunch of junctions and stuff. Suggestions? Any thoughts? Yep.
Find the resistance for the light bulb.
Oh, how can I find the resistance for the mystery light bulb? Why? There's one. I think you've seen it, but I want to make sure everyone else has seen it. What else do I know in that bulb? I know it's 3.5 watts. What else do I know? Ah. I know current equals 0.35 amps. If I know 2, I know 4. You know what? I also know the voltage drop going through here. Power is VI. It's going to be power divided by... See, this is why I may have made up an impossible circuit. We'll see. Power divided by current Is 3.5 divided by 0.35 10 volts? Is it? Really? You guys aren't doing it? What's that? 10? How high is my chairlift? Can I possibly have a ski hill that's 10 volts high? Scribble, 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 scribble. Scribble, 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 scribble. Make the current larger, Mr. Dueck. Make it larger, and that way when you divide, it'll be better. Okay, good point. Good thinking. Let's do a current of 0.6 amps and 0.6 amps. So now Paige would be saying that's 0.6. The voltage would be power divided by current. Please work out half decent. 5.83333. And the resistance in here is going to be, you know what? I don't know if I need to find. You good? Can you put it face down on top of the correct block? I don't even know if I need to necessarily find that. I think I may have enough, because how high is my chairlift, the maximum theoretical, if I ignore the bump at the end? 9 volts. How high is the only major ski hill? 5.833. How high must the only other hill, the bump at the end of the chairlift, be? It's got to be 3.1666, 3.17. This has got to have a voltage of 3.17 volts. And I already know the current, 0.6 amps. You know what? The internal resistance is going to be V over I. It's going to be this divided by 0.6. 5.3 ohms. Turns out, and by the way, yours would have been fine too. Turns out I didn't need to, though. I could get there quicker. And again, you'll notice I'm using terminal voltage. I really, even at the beginning of my tutorial, I said, you know what? There's 2 equations. There's this one. These are the 2 I use. There is that terminal voltage plus or minus equation. I hardly ever use that. I used to. Before I really wrapped my brain around this, I taught everything formulaically, and oh, I'm not joking. Here's how I used to teach all of these. We would solve them all with systems of equations like this. So we would do a loop, and I would label every current, I1, I2, I3, and you would get a lovely system, and now you could solve by substitution. And to be honest, the way I've taught with ski hills, I think most of you would solve this in 3 lines as opposed to that. So this is one unit I think I've gotten way better on. You want to try that one just for fun? Sure, we can. Let's see if we can do it shorter. That was the newer one, number 1. Oh, hang on, there was a part B here. Ah! This is the kind of using principles of physics question. By the way, the answer 0.63 is for the original the original current that I changed. The light bulb is replaced by a lower resistance, brighter light bulb. Okay, let's see. Oh, I should answer the question here. Little r equals 5.3 ohms. Let's do a using principles of physics, right to explain. So let's suppose I replace this with a bulb of lower resistance. What will happen to your terminal voltage? One way to do this would be to calculate the resistance of this bulb, make up a number that was smaller, and now recrunch everything. Let's see if we can do this intuitively. If R, what did we call that? R bulb smaller, what happens to the total overall resistance then in this circuit? Smaller, bigger, or stays the same? Because I think the total overall resistance is the big resistor plus the little resistor, and so it just got smaller. Right? Is that okay? Oh, and V total equals I total, R total. You know what? Total current is going to be V total divided by. So if this gets bigger, and remember my total voltage, this is really my maximum theoretical chairlift. What would happen? It's after school, I'll live with it. What would happen to the new total current? Bigger, smaller, or stays the same? Let's see, this hasn't changed. This just got smaller. So if you're dividing the same number by a smaller number, what happens to your new answer? Yeah. Okay, so now let's go here. If this current got bigger and this resistance hasn't changed, I increases. Little r, because they said you haven't changed the battery, so little r is still 5.3 ohms. What happens to the size of the bump at the end of the chairlift? Right? And the terminal voltage is chairlift minus bump. Bump? Bump. That was dumb. That was dump. Yeah. Bump. Getting my P's and B's mixed up. So instead of 9 volts minus 3.17, it's going to be 9 volts minus a larger number. You know what? My terminal voltage is going to be less than before. And in terms of a proof, there you go. Again, that's purely algebraic. Emily, you could certainly crunch the numbers, but I was able to reason my way there. You know what? If my overall resistance, my total resistance gets smaller, current goes up. Oh, and if I got more current going through this same resistor, this voltage drop is bigger. My terminal voltage, my actual measured voltage, is going to be smaller. That's kind of counterintuitive to people. Again, when you hook up a battery and you put a smaller resistor on, you're actually getting less voltage than you were with a bigger resistor. Why? Because you're getting a higher current. You're draining the battery faster. Okay. Yeah. That would be lovely. And in fact, if you did a purely algebraic proof, after wiping away the tears, I'd probably put a little happy face or a smiley face or write a little nice. I have no problem. I made sure when we were marking provincial exams, I double-checked. Can they just make up reasonable numbers and crunch them? Yes, absolutely. But the nerd within me, the word we use in math is an elegant proof. If you give me a nice elegant proof with no numbers, in fact, there's probably a shorter proof algebraically than the one that I just did lurking out there. Oh. Is that all right? Hey, let's try that question number 1 that I used to teach so hideously. This one here. So this used to be a classic 7 marker. Let's try our strategies. Hey, what's the first thing I look for? Really? What's the first thing I look for?
2 things. Which one is
Total current? Because, by the way, our whole strategy for the next 10 minutes is going to be, let's find the total current. So I checked to see if they gave it to me. You may have noticed, if they give you, in fact, you may have noticed, if they give you any current anywhere, often the question totally falls apart. They didn't give it to me. I look for anything with 2 or any current anywhere. They didn't give it to me. You know what? My strategy is going to be rewrite this as a single solitary resistor. And then I'm going to go I total equals V total over R total, which sounds to me like I'm trying to find I total, total current. Parallel. So 1 over R parallel equals 1 over 12 plus 1 over 8. 1 over 12 plus 1 over 8. Don't forget to, 1 over 2, Mr. Dueck. 1 over 12 plus 1 over 8. Don't forget to reciprocal your answer. 4.8. So the mathematical equivalent, some of you are probably good enough that you don't need to do a sketch. I'm going to do a really quick, well, you know what? Actually, I'll be honest. On a test, what I would probably do is this. I would say that's the same as that. That way I've got my circuit diagram, my original one, nice and clear. And that way I hope you can see, Emily, that I now have everything series, series, series quite nicely. In fact, I can tell you our total right now. Our total would be 4.8 plus 10 plus 12. 10 and 12 is 26.8 ohms. Oh, now what? I total equals V total over R total. You don't have to write that if you want to go straight to the numbers. If you wrote I total equals 80 over 26.8, that's perfectly fine. Is my 26.8 right? I have some people who frown. Yeah, I did. Meh. Oh, you know what? 2.985, because there's a 0 after that. I think 4 sig figs will be good. 2.985 amps. Okay. 2.985 amps. 2.985 amps. Do I know 2 on both of those? Well, then heck. Times 12. This is third. You know what? Let's use the 2.985 so that I'm consistent. Normally I like to use the non-rounded off value, but here 2.985 times 12, I times R, 35.82. 29.85. That one I can do in my head because it's times by 10. How many volts am I starting with? 80. So I guess each one of these must be 80 minus 29.85 minus 35.82. 14.33 volts. Now, oh, I know it's asking about the 8 ohm, which is R4. I know 2 things down there. I know all 4. They want the power. Power, I know voltage. And now you could find the current, by the way. I equals V divided by R. And then you can use the VI. But just to refresh my memory, I think I can say power equals V squared over R. It's going to be 14.33 squared over 8 squared over 8, and let the answer be 26 watts, which it is, 25.7. Yeah, I've improved in teaching this, I think. That, as compared to, oh, I closed the answer key. It was too embarrassing. Where was it, Mr. Dueck? Oh. Yeah. That looks a little more confusing. Let me just look at what I covered last time. So we did that. Are you guys are okay with terminal voltage? It looks like my last group, you know what? Because I switched the lessons with you guys, didn't I? I did terminal voltage and then I did one more after that. Looks like last year they were asking me all about terminal voltage. That's probably because it was the last lesson I did in the unit. Nobody did the homework. So I'm doing like a gazillion of these. Oh, this one actually looks like it might overlap something that you'll see tomorrow. So that's number 29, Mr. Dueck. Okay, let's go see. Sure, this works. Clip. And then this also has a part B. Clip. And it's the part B that I'm giving you a little bit of a hint, hint, wink, wink, nudge, nudge for. The cell shown supply, oh, they gave me a key, 1.8 amps to R1 and R2. So this is 1.8 amps. Holy smokes, they gave me our total. What else do you know right away? Voltage. So what's voltage in resistance 1? Can someone go 1.8 times 2.5? And can someone else find the voltage in resistance 2? In resistor 2?
4.5 for R1.
Sorry?
First is 4.5.
Even?
Yep.
Second one? Even? So why can I tell you that the terminal voltage has to be 11.7 volts? Because I know that whatever height this is, minus the chairlift, the only two heights that are left added to 11.7. You know what? When you got off the chairlift and went down the tiny bump, because that's what your terminal voltage is, it's chairlift minus the tiny bump, apparently after that you were able to ski through 11.7 volts. So it must be 11.7 volts. In fact, you know what? I'll bet you the EMF, this is probably a 12-volt car battery or a 12.1 volt car battery or something like that. You probably could have found it using an actual formula. You probably could have actually gone, oh, now I know the current in here is also 1.8, and you could have gone V terminal equals EMF minus IR. Oh, no, you don't know the EMF, so I guess you couldn't have used that equation there, could you have? Oh, but what are they asking me to find in part B? In part B, they're asking me to find the EMF. What's the voltage drop going through the battery in this internal resistor? I can do that in my head. It's half of 1.8 because it's 1.8 times 0.5. I think I lose 0.9 volts going through there. So, how high must my chairlift have been originally? Is that okay, Dorothy? Yep. Supposing, suppose I increase R1, make it bigger. What would happen to the terminal voltage, and what would happen to the EMF? Oh, they use lowercase for EMF. The second question should take you 1 second to answer. What would happen to the EMF? Too slow. What would happen to the EMF? Too slow. If you change the ski runs on a ski hill, what happens to your chairlift? Nothing. EMF is what's printed on the side of the battery, and what I've been trying to tell you is that EMF what changes is not your chairlift height. What changes is that little bump at the end of the chairlift, how much you lose going through the battery. What changes is your terminal voltage. That's what we're going to have to look at here. If this got bigger, if that got bigger, your total resistance would increase. Yes? So your total resistance would go up. What would happen to your total current? So let's write this down. R1 gets bigger, comma, R total gets bigger, comma, and I know that I total equals V total over R total. What would happen to your overall current? Get smaller. Why am I spelling bump like dumb? Good gosh, there's a Freudian slip. You say one thing, but you mean another. V bump equals I times little r, and it's I total because in our circuits in Physics 12, the total current's almost always going through the battery, unless we have two batteries in parallel, and I already told you I'm not going to test you on that. So what would happen to the bump at the end of the chairlift? Get bigger or smaller if the current got smaller? What happened to I total? What did we just say? It's got smaller. So what happens to the bump? It gets smaller. So your terminal voltage is bigger because the bump is how the terminal voltage is what's left after that bump. EMF is constant. Turns out, and this is kind of counterintuitive, throw a bigger resistor in this circuit, your voltage that you measure across the battery would go up, not down. Why? Oh, because the total current running through this went down. And I think that means the battery would last longer. Yeah, of course that means the battery would last longer. Because if you have no resistance, we call that a short circuit. You have a huge current and it burns your battery out in about 2 minutes. If you hook up a battery with a wire to its own end, it burns out in a few minutes. Counterintuitive, because people want to say, well, bigger resistance, that's like a bigger appliance. Wouldn't that make things last shorter? No, because it reduces the amount of current you can get through your system. Turns out it lasts longer. A little weird. Wow, apparently I did some scholarship questions here. Or maybe someone had a question. You know, I think someone asked me about scholarship number 10. So let me see. Oh, I am going to ask you on your test about the correct placement of a voltmeter and an ammeter. So what did we say about that? Let me see if I can find a picture of one in my... Oh, heck, let's go to the old physics review. Let me see. Stop me if you see a letter V with a circle or a letter A with a circle inside a circuit. Yeah, I'm going fast. Oh, hey. There's a voltmeter. Okay. Is that placed correctly? Yes. Voltmeters you always want to have in parallel because what's my analogy? What if I said voltage is kind of like on a ski hill? You're right, Dorothy. Sorry? No. Skiers is current. What if I said voltage is? Someone said it. It begins with letter 8. It's like the height. Well, Jake, the only way you can measure the height is to have two separate locations and ask how high between them. Like that. With a voltmeter, you have to touch it to two portions of a circuit in parallel, and it'll tell you the difference in height between those two portions. Okay? Compare that with an ammeter. If I had an ammeter set up like that, see, an ammeter is trying to measure how many skiers, but if you had it set up like that, couldn't a whole bunch of skiers go through here and the ammeter would never know? That's why you never want to set up an ammeter in parallel. You want an ammeter to be in series. You want to force every skier to go through it. Let me see if I can find one that's got both. Ah, here we go. Perfect. This is the kind of multiple choice question you'll see. So it says, in the diagram above, I need to make it a little bit smaller so it'll fit on the screen. Where could you insert a voltmeter and an ammeter so as to measure the voltage across resistor R and the current through it? Okay. First of all, what location could you put a voltmeter at? Location 1 or 2 or 3 or 4? Yep. Location 4, because that would give you, oh, you know what? If we shake hands and split up, and there's only one hill, only one resistance on this ski hill, these two hills have to be the same height. And Dorothy, what have I said voltage is the same as? Height. So 4. By the way, whenever you're answering these, hopefully by now you've learned you go like this then. No, no, yes, yes, and then you zoom out again. Ammeter. Which of those locations would measure every single skier that went down that ski hill? Why would 2 be wrong? Cannot some skiers after leaving 2 go that way as well as some go this way? So this would not measure how many ski. You know what? The only gate, the only ammeter, you can think of an ammeter as a ski gate, it's got to be location 3. That would measure all of the current, all the skiers that went down that ski hill. It doesn't have to be in front of the ski hill, it can be after the ski hill, but I'm telling you, every single current, every single charge, every single skier that goes through R has to go through gate number. Oh, you can't see, that says positive, that says negative, although it wouldn't make a difference anyways. No, if the current was going this way, here you'd have some skiers from there, that hill, and some from that hill. This would not give you an accurate reading no matter what for the current. Right? Because you have junction joining in.
If it was the other way, wouldn't it be like they have all because they went back?
They all have to go through 2, but every single skier that goes through there didn't have to go down this hill. Some could have gone down that hill, so I wouldn't know how many skiers went down this hill. Right? If downhill was the other way, you can go this way, but look, some skiers could go this way. I humbly suggest that blue-green is through there, but there's no green on the middle run R, but I'm measuring some green skiers in resistor, in ammeter number 2. No? Trust me. Huh? Okay, let's make up numbers. Okay, let's make up numbers. Okay? Give me a nice number for total current. Higher. 10? Okay. So, 10 amps leaving the battery. I'm just making up numbers. Let's suppose 3 amps go this way. How many amps have to go this way? You're telling me that this is going to measure 3 amps right there, the same as going down that hill? I'm arguing that I got 7 amps, I got 7 amps, I got 7 amps, they're joining together. That's going to measure 10 amps, not 3 amps.
Who said it's going to measure 3 amps?
It's saying what would measure the current through resistor R. I'm telling you, there's no way that ammeter 2 can possibly measure the current through resistor R. It's going to measure a totally different current.
Yeah, we were going to ask for the question.
Oh, I'm sorry. I thought I was teaching physics 12, not reading 8. My bad. I will never make that mistake again. I will not overestimate your intelligence again, I promise. But having said that, that was a good discussion, okay? Was that okay for, in terms of, there's going to be one multiple choice question where I say, hey, which of these is labeled correctly? Yep.
And you, under ammeter, you checked 2.
I checked 2. That should have been an X right there. There you go. I circled the right answer at least. Yes?
Yeah.
Okay. There's going to be, I think, probably one question with a switch. So let's see if I can find a switch question. And apparently I did, and apparently it's from my old review. So let's go find it, Mr. Dueck. I'm looking for a 6 volt at the top. Nope. Sure, here. Did I do the whole question? Sure. Here's a good theoretical using principles of physics right to explain question. By the way, I'm kind of making the assumption you guys are okay on the basics of the basic stuff. I'm just doing the obscure, nasty stuff, right? So if you're getting worried, believe me, most of the test is going to be fairly straightforward. For most of you. let's just, you know, how about Jake? You help me along with this one, okay? Jake, my friend, can you read the question to me, please? Starting with, not the instructions where it says use the following, but in the circuit. Start reading there, please.
Shown above.
Yep.
What is the effect on the ammeter?
Stop. Where's the ammeter? Okay, up there next to the 6 volt. Gotcha. Keep going.
Correct click as well.
Yep.
And the voltmeter readings when the switch is closed.
Okay. Let's. Do you want to deal with ammeter first or voltmeter first? I don't care, but.
Volt.
Okay. I think. Thank you, Jake. I might choose to look at the ammeter first because look at. I'll be honest. Here's. It probably didn't matter too much, except I'm looking at that ammeter. Look where it's placed. Isn't it measuring total current? And haven't I said, you know, when in doubt, what do you want to try and find first? Let's see if we can reason our way to that. Okay? So right now, with the switch open, what's my total resistance? Is that 3 ohm part of the circuit at all? No. So what you really have is a 4 and a 2 in series. Convenient, because what's 4 plus 2? Yep. Right now, let's do, you know what? If I was answering this, I would probably go open, closed. If this was a using principles of physics right to explain. Open, total current is a convenient 1 amp. I went 6 divided by 6 in my head. I didn't lose you, did I, Jake? You okay? Now, when you close that switch, really what you're asking is, what happens to that? Actually, that's not what you're asking, because total current is chairlift divided by total resistance. What you're really asking is, hey, does that get bigger or smaller? Because whether that gets bigger or smaller is what's going to determine whether total current gets bigger or smaller, because that 6 volts is going to stay the same because they didn't give me any internal resistance. That 6 must be the EMF. You could crunch the numbers. Mabot already is. He's going 1 over 3 plus 1 over 2 and then reciprocaling that. I can do better than that. Remember, I actually told you guys, anytime that you have a parallel resistance section, that when you combine it into one, the answer is always going to be smaller than the smallest resistor in there. What's the smallest resistor in here? I'm telling you, when you combine it, the answer is going to be less than 2. Which means our total is going to be less than 6. Right? Which means that got smaller. Which means that got bigger. No. Okay. And it would take you 10 seconds to actually crunch the numbers as well. But let's see if we can do this without numbers. Voltmeter. Okay. So right now, what's the current with it open? 1 amp. So Jake, if V equals I times R, and R is 4, and I is 1, can you go I times R in your head without a calculator and tell me what the voltage drop is in that resistor? What is it? 4? What about here? How high? How high? How high? We're doing open. Yes. 6, 4, 2. Okay. By the way, they've deliberately picked some nice numbers so that you can do this in. All of us, yes, even can do this in our head, right? Now, Jake, my friend, what did you just tell me happened to the total current when we close the switch? It gets smaller, right?
Yeah.
Right? Remember? I know it was 3 minutes ago.
The ammeter?
Yeah. Which is the current.
Yeah.
Gets smaller, yes? So instead of 4 times 1, it's going to be 4 times a smaller number. You agree with me?
Yeah.
So instead of having 6 take away 4, 2 volts in each of these, it's It's going to be 6. Take away a smaller number, more than 2 volts in either of those, because you can shake hands and split up Dorothy and go that way or that way. I'm telling you, the voltage here and here must have gotten bigger, slightly. Do you want me to rephrase that? I've done it all intellectually. I don't mind crunching numbers or doing it again. Did you follow my argument? Are you lying?
No, I actually.
Okay. Did you follow my argument? Right? Oh, and we know both of these must have the same voltage because shake hands, go this way, go this way. We want no current to go through. By the way, for what it's worth, in real life, if you build a voltmeter, you try and design it with an infinite resistance because you don't want any skiers to want to go up this hill. Because if any skiers go down this hill, that changes the whole circuit now, and it's now not measuring accurately. So in theory, voltmeters have infinite resistance, and in theory, what do you think you want the resistance of an ammeter to be? As close to 0 as possible, because if you accidentally add an extra ski hill, that's a whole different circuit now. For what it's worth, if you get any of you get into electronics. Okay. So we said that increases. Okay. Now, what would that mean? Look up. What would that mean? Since power is V squared over R, when you close this switch, brighter, dimmer. Turn on in the first place. Right? The 2 ohm bulb would suddenly get brighter because that hasn't changed, but you just told me that when I close the switch, it gets a bigger voltage. The 4 ohm bulb would suddenly get dimmer because that hasn't changed. It's still 4 ohms, but you just told me that it gets less voltage. Oh, also you can think of it in terms of it gets less current. Is that all right? Stick around for 2 more minutes, just hang on. I'm just kind of rambling now. I think I've given you hints about the using principles of physics right to explain. I'll do a quick, I like this question, I guess, but you know what? Really, if you want to know which questions I like, almost any circuit that they're asking you to solve on the big review, because I tried to throw a bunch on there. Are there any that jump to my mind? Let me see here. Oh, well, in terms of ammeters and voltmeters, number 1 is a great example of that too, okay? You don't need to worry about question 3, or did I cross out question 3? Okay. Transformers, we're going to be doing the very, very last unit, so don't freak about that. This was from the provincial, and it would be fair game if I'd covered transformers at the end of the year. This would be a fair game question. By the way, they're commonly used in any device where you... B is the answer there. Anyhow, I think. That's fine. So here would be an example of the kind of question where you're actually going to use current equals charge divided by time. You know how you can tell? Because holy smokes, there's coulombs, and holy smokes, there's seconds. So it's kind of obvious. But I'm pretty sure I gave it to you as a multiple choice variation on this. Heck, even I think it was the first, I think it's question 1. Don't quote me on that. I'm going from memory now. So something like number 9. I guess I'll say this. You can probably expect most of the circuits will have an internal resistor in the battery, and so it's a terminal voltage or an EMF involved. So I like number 12, but I'm pretty sure the odds are I'd also give you an internal resistor right there. Uh, 14 is good. So 15, I've tried to give you a suggestion on how I would handle it. Now this one has no numbers. The one we just did, Jake, had 6 volts. And you know what? Make up reasonable numbers. A good voltage to go with when in doubt for a battery. 36, because lots of numbers go into 36 when you're going V over I or V over R. That's a nice one. And in terms of resistors, I usually use 2s, 4s, and 8s, because when I take those as reciprocals, they often work out nicely. I try and avoid anything that has a 3 in it, because the reciprocal of 3 is always a repeating decimal of some type, which makes it yucky. So, little tricks of the trade. Yeah, 16 is fine. Sure, 18. I think 19 is the one that I hate. Let me just double check. And I want to talk about it so you don't freak. Okay, Dorothy, come see me. Is your test tomorrow?
Yeah.
Do you want me to print this up for you?
No, it's okay.
Oh, you're good?
Yeah.
I'll put it online if I can too. Yeah, you know what? No, actually, this isn't the one that I hate. This one I'm okay with. There's one question where, due to sig figs, when you start with the EMF and when you round off the terminal voltage, you get the same answer, which doesn't make sense to me because when you ski down the bump, your terminal voltage should be smaller. So it's not this one, it's another one, or I may have finally nuked it. Anyways, that one's good. 20 again, so there's going to be one kind of a using principles of physics, and it's going to be something to do with adding a resistor or opening and closing a switch. One of those two options. I think 20 was a fairly nasty one. I think 20 I ended up solving it without walking through everything. I think I did a process of elimination. Going from memory here. Sure, 21. This is the question that got, oh yeah, this question got nuked. This used to have a part B. I think there's only a part A that I copied. Yeah, there was a part B. Part B was when they closed this switch, and Paige, this goes back to your earlier question. There was no resistance down here, so kids were supposed to realize that this bulb would be totally shut out, but that's not officially part of Physics 12, so don't freak out about it. If you're wondering, why is that switch there? It was for a part B that got tossed. 25 you can cross out. If I haven't done that already. That's going to be the transformers, which happened later on this year. Oh, this is the one that I said was a bad question. Because the EMF ends up being 1.5 volts, and the terminal voltage ends up being 1.5 volts if you go to 2 sig figs. It's 1.54 and 1.47 to 3 sig figs. I just wrote bad question because they should have gone to 3 sig figs in their answers, for Pete's sakes. Because I had a bunch of kids, Mr. Dueck, I thought you said the terminal voltage is less than the EMF because you've gone off the bump, and I'm getting 1.5 and 1.5. And I went, yeah, that's a stupid question. Yeah, 28's good. What's the part B? Was there a part B? Oh, yeah. What was the part A? Oh, yeah, sure. 28's good. 32 is good. $36 is good. $37 voltmeter, ammeter placement, sure. Oh, sure, 39, find little r. There's a nice twist. I will be, there is a question where I'm going to ask you to find some kind of a resistance, whether it's the internal one or one of the outside ones. It's going to be one of those. You can cross out number 40. Consider the circuit shown below, blah, 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 blah. Yeah. By the way, so looking at number 44, I talked about ways so you don't have to memorize every single graph. We're graphing voltage on the y-axis, current on the x-axis. So they said find the slope. I went rise over run. What is the slope represent? Well, I said it's voltage divided by current. What the heck is V over I? Oh, it's got to be resistance. So you may recall, like 3 months ago, I did a lesson on, hey, if they're asking you for the slope, divide the units or divide the variables, and you'll almost always figure it out. If they're asking you for the area, multiply the units or multiply the variables, and you'll almost always figure it out. I did not know that a graph of I don't have memorized that a graph of voltage versus current is the slope is resistance. I don't need to. Figure it out in 2 seconds. We're near the end here. Yes, yes, yes. Make sure you know the difference between conventional current and electron flow. Conventional current, which way is the positives would flow if they could. Electron flow, actually in the negative direction. Yeah, here's another graph one. Area, so I said the area is going to be I times T. I said I have an equation with I and T in it. Why don't I get the I and the T next to the same side? And I said, oh, I think Q equals I times area. It's got to be the charge. Probably the total charge stored in the power supply, battery, or whatever the heck this was. And then there's the scholarship ones. This one was pretty tough. I had to do a system of equations. I don't think 55 is really that much of a scholarship. I mean, it was tricky-ish, but it's just one battery and a bunch of resistors. The only issue is at the end they wanted you to find the height change between Y and X, so I just went skiing down those 2 hills and added them up. So there you go. Any other questions? Hope that helped. Who wants a copy? All of you? 1, 2, 3, 4, 5, 6, 7, 8, 9.